Hello all. Welcome to the video lecture for Chapter 4, Section 1 of Calculus 1. Today we're going to be talking about extreme values on closed intervals. So one of the most important applications of the derivative is its use as a tool for finding the optimal or best solutions to a problem. So if we have a function, let f be a function with domain D, then f has an absolute maximum value on D at a point C if all f of x's are less than or equal to f of c for all x in the domain. In other words, if the y value is larger for that point C than it is for all the other values on the graph. Similarly, our graph will have an absolute minimum if the y values are greater than all the other y values are greater than the y value at our point. These maximum and minimum values are called extrema of the function f, or extremes of the function f. Absolute maximum or absolute minimum also are referred to as global maxima or global minimum. So here's a few examples of the idea of absolute maxima or absolute minimum. So the absolute extrema of the following functions on their domains can be seen in figure 4.2. Each function has the same defining equation y equals x squared, but the domains vary. So in this first case, the domain is everything, negative infinity to infinity. So in this case, there's only an absolute minimum here at this point. Everywhere else on the graph, there is no maximum value, but every y value is larger than or equal to that y value there. So we have an absolute maximum at that point, 0, 0. Or absolute minimum, of 0 at x equals 0. If we close the interval to 0 to 2, now we both have an absolute maximum and an absolute minimum. Here is our absolute minimum. At x equals 0, the minimum is 0. And at x equals 2, the maximum is 4. However, if we only include the upper endpoint here, then we would only have a maximum, because this point is now no longer in our domain, so our maximum is only at that point. And last but not least, if I don't include either of the endpoints, then we have no absolute extrema, no absolute maximum or absolute minimum, because neither of those points are included. So another theorem that goes along with this is the extreme value theorem, which says that if f is continuous on a closed interval a to b, then f attains both an absolute maximum value m and an absolute minimum value lowercase m in a comma b. That is, there are numbers x sub 1 and x sub 2 in a comma b such that f of x sub 1 is equal to the minimum and f of x sub 2 is equal to the maximum. And that all other y values, m is less than or equal to f of x, which is less than or equal to capital M for every other value of x. In other words, all other values of x give a y value that is between those two. So we can also define local maximum and local minimum. So a local maximum value at a point C within its domain D if f of x is less than f or equal to f of c for all x lying in some open interval containing C. So if you can make an interval around a point, then we can, in which all the other values are less than that y value at C, then that's a local max. Similarly, a function has a local minimum if the same thing happens except in a minimum. Local extrema are also called relative extrema. So a theorem that's really useful here is that if f has a local maximum or minimum at an interior point of C of its domain, and if f prime is defined as C, then f prime of C equals 0. So in other words, all local maximum and local minimum are at points where the derivative equals 0, which should make some sense, because what happens when the derivative is 0? Well, that means the slope of the tangent line equals 0. So that would be a horizontal line, and that's where we would expect to have maximum or minimum. An interior point of the domain of the function f where f prime is 0 or undefined is a critical value, critical point. So notice that this definition doesn't necessarily work in both directions, which is why we define the idea of a critical point. All local maximum and local minimums are at points where the derivative equals 0. However, not every place that the derivative equals 0 do we get a maximum or a minimum. So all our local and maximum and minimum will be at critical points, but not all critical points will be maximums or minimums. So if I want to find all the critical points of a function, what I need to do is find the derivative. So we could find the derivative of x here by using the quotient rule. So this would be x minus 2 times the derivative of 2x minus 2x times the derivative of x minus 2 all over x minus 2 squared. So f prime of x equals x minus 2 times 2 minus 2x times 1 over x minus 2 squared. So f prime of x equals 2x minus 4 minus 2x over x minus 2 squared. And then the 2x and the negative 2x cancel, so f prime of x is negative 4 over x minus 2 squared. And so now we can set that equal to 0 and look for any critical points. So if I set that equal to 0, then we get negative 4 over x minus 2 squared equals 0. And if we try to solve that, we get no solution. So if we multiply both sides by the denominator, that cancels, multiplied by 0, and there are no solutions to this. So this has no critical points. Okay, so there's one example of how these steps would work. So we could try another one. So we start by finding the derivative of g. So g prime of x. In this case, we need to use the chain rule. So the derivative of a square root is 1 over 2 times the square root of 2x minus x squared times the derivative of the inside. So g prime of x equals 1 over 2 root 2x minus x squared. Times 2 minus 2x. And so if we multiply that all together, we get g prime of x equals, we can cancel out a 2. So 1 minus x over the square root of 2x minus x squared. And then to find where it's equal to 0, we set the function equal to 0. So f prime of x equal to 0. So that's going to be, g prime of x equal to 0. So 1 minus x over the square root of 2x minus x squared equals 0. Multiply both sides by the denominator, and you get 1 minus x equals 0. So add x to both sides, and we get 1 equals x. So one critical value is going to happen at x equals 1. And so we want to know is what's the ordered pair that goes with that. So now what we need to do is find g of 1. So we plug that back into the original function. So 2 times 1 minus 1 squared. So that's 2 minus 1, which is 1. So the square root of 1 is 1. And so our critical point is at 1, 1. Now, I did forget something for the first one, and I'm going to do it here for the second one too, which is I forgot about the fact that critical points also happen when the derivative is undefined. So what we want to do too is we want to know, well, when is this derivative undefined? Well, the derivative is undefined when the denominator equals 0. So in this case, that's the square root of 2x minus x squared equals 0. So that's 2x minus x squared equals 0 when we square both sides. Factor out an x. And we get x equals 0 or x equals 2. And so now, once again, we can plug those values back into the original function and see what we get. So if we plug in 0, we get 0. So we get a critical point at 0, 0. And if we plug 2 back into the original function, we get 0 as well. So another critical point is 2, 0. Okay, so that's the idea there. And like I said, I forgot to do that with the one previously. So if we go back to this one, I also want to look at when is this one undefined. So I look at the denominator again, right? Because if the denominator's undefined, then we'll have, if the denominator is 0, then we'll be undefined. So we let the denominator equal 0. So x minus 2 squared equals 0. So this isn't going to be correct. We are going to have critical points. We're not going to have any critical points from there. But solve this and you get x equals 2. Plug the 2 back into the original function. And, well, what happens there is when I try to plug 2 back into the original function, I get undefined. So I'm not going to have a critical point. So I guess I can take this back. I am actually going to have no critical points. So when we try to plug 2 back into the function, so f of 2 is undefined because we get 0 in the denominator. So there are no critical points for this first one. Okay, so that's the idea. So you find the derivative, see when the derivative equals 0, and see when it's undefined, and those will tell you where your critical points are. So what I'd like you all to do now is try the 2 problems on this page. So go ahead and pause the video for a moment, try these 2 problems, and when you hit play again, we'll go through them together. Okay, so now that you've had a chance to try these, let's just run through the answers real quick. So we, as we said, start by taking the derivative. So f prime of x, in this case, would be 12x minus 3x squared. Then we set that equal to 0, so f prime of x equals 0. So that's 12x minus 3x squared equals 0. And we can solve this one by factoring. So factor out a 3x, and that leaves us with 4 minus x equals 0. Set those both equal to 0. And you get x equals 0 or x equals 4. And now, once we've done that, we can plug those values into the function. So we can find f of 0 and f of 4. So f of 0 is just going to be 0, and f of 4 is 6 times 16 minus 64 is 32. So we get f of 4 is 32. So our critical points are 0, 0, and 432. And notice in this case, we there is nowhere where this expression is undefined because its derivative is a polynomial, and so we're done. Okay, so that's the idea there. Same idea for the next one. You have 2 options on how to do the derivative. You can either use the product rule and the chain rule, or you can multiply this out. It's probably actually going to be easier to do this problem if we use the product rule and the chain rule. Maybe, we'll find out. But that's what I'm going to go ahead and do for this one. So this would be g of prime of x. Whoops, sorry. I accidentally clicked on the colored pencil option. So let's try that again. So g prime of x equals x minus 1 squared times the derivative of, I'm actually going to change my mind. Let's go ahead and multiply these out. I think this will be easier just to do it as a single derivative now that I'm looking at it closer. So if I multiply g of x out first, so this will be g of x is x squared minus 2x plus 1 times x squared minus 6x plus 9. And then we can multiply that out again. And so that's going to be x to the fourth minus 8x cubed plus 22x squared minus 24x plus 9. Okay, and then we can take the derivative of that. So g prime of x is 4x cubed minus 24x squared plus 44x minus 24. And then we can set that equal to 0 and try to solve. So if we set this equal to 0, it's 4x cubed minus 24x squared plus 44x minus 24 equals 0. Divide everything by 4, and you get x cubed minus 6x squared plus 11x minus 6. And now here's an opportunity where we may want to use our graphing calculators to help us out. And in fact, we can talk a little bit more about how we can use the graphing calculators in general. But if I wanted to know where this is equal to 0, I could try and use my graphing calculator to help me solve this by graphing that function. So if we open our ClassCalc apps, go to the graphing function, we want to graph y equals x to the third power minus 6x squared plus 11x minus 6. Let me go back to my notes real quick just to make sure I got that right. Yep. Okay, and so if we do that, we can see these points are where it's equal to 0. 1, 2, and 3. Okay, so if we come back to our paper here, we solve this and we get from the graph, we can see that x equaled 1, 2, and 3. So then what we need to do is just like the one above is find f of 1, f of 2, and f of 3. In the original function, or actually, sorry, I should say g of each of those. So g of 1 is 0, g of 2 is 1, and g of 3 is 0. So we get the ordered pairs 1, 0, 2, 1, and 3, 0. And if we go back and we graph the original function as well as the function we just did, we can see what those critical points look like. So if I graph x minus 1 squared times x minus 3 squared, you can see on our graph now that at the point 1, 0, we get a minimum. At 2, 1, we've got a maximum. And at 3, 0, we get a minimum. And one of the nice things about this ClassCalc app is as long as it will label the maximums and minimums for you. So as long as they're integers, you wouldn't necessarily need to use derivatives to find these local maximum and minimum. Where we run into trouble is when our maximum or minimums are not integers, are not numbers that we can easily recognize, like the square root of 3 or something like that. So anyway, so there's our local maximum and minimums for that. So now we want to talk about the last thing in this section is how to find absolute extreme on a continuous function f on a finite closed interval. So one of the theorems we just looked at says that when we have a closed interval, we will have absolute maximums and absolute minimums. So what you want to do is you want to find all critical points of f on the interval, and you want to then evaluate f at all critical points and endpoints, and then you take the largest and smallest of these values. So your options for where the absolute maximum or minimums are at the critical points and at the endpoints. So what we want to start out by doing is the same thing we were doing on the last page, which is we start out by finding the derivative. So f prime of x in this case would be 1 over x squared, right? The derivative of negative 1 over x. You take the exponent times the opposite of the exponent, so the opposite of 1 times the expression, so negative 1 times negative 1 is positive, and you add 1 to the exponent to get 2. Then we can set this equal to 0, and if we do that, we see that there are no solutions. So in this case, there are no endpoints. So the only no critical points. So the only x values we want to look at are the endpoints. -1 and -2, and then we find f of those values. So f of -1 would be -1 over -1, which would be +1, and -2 would be 1 over 2. So then the largest of these values is the maximum. So in this case, the maximum is -1, 1, and the smallest of these values is the minimum. And so that's really all there is to that. So let's try another one. So we try the same thing with the secant. The first step here is to find the derivative of the secant. So the derivative of secant is secant x times tangent x. Okay, and so now we set that equal to 0. So secant x times tangent x equals 0. And we have two things multiplied together to get 0. So those will be 0 when either of them is 0. And so one of the things you want to remember about secant x is 1 over cosine x. So there's actually no way for this to be 0. So the one on the left has no solutions. And then we can look at the one on the right. And for the one on the right, tangent of x is 0 whenever sine of x is equal to 0. So that would be at 0, and it would be at pi, it would be at negative pi. But the only ones of these that are in our interval from negative pi over 3 to pi over 3 is 0. So that's the only one we need to worry about. So we do the same thing we did up here. So we do x, we do the critical point, which is 0, and then we also plug in negative pi over 3 and pi over 6. And then we do g of those numbers. So secant of 0 is 1 over, these are all 1 over cosine of these. So cosine of 0 is 1, so 1 over 1 is 1. Cosine of negative pi over 3 is I think root 3 over 2, but let me check that. Oh, actually, sorry, it's 1/2. So, yeah, so it's 1/2. So 1 over 1/2 would be 2. And then cosine of pi over 6 then would be root 3 over 2. So 1 over root 3 over 2 is 2 root 3 over 2. Over 3, sorry, not over 2. Over 3. And so we just need to decide which of those is the largest and which of those is the smallest. So the one thing that might be helpful here is to do 2 root 3 over 2 as a decimal. So we can get an approximation for that. So that's 1. This is approximately 1.15. So that would mean the minimum is 0, 1, and the maximum is negative pi over 3, 2. Okay. So let's try one more of these together, and then I'll have you all try some, and then we'll be done for today's video lecture. So step 1, as always, is do the derivative. So in this case, we need to use the chain rule. So the derivative of a square root is 1 over 2 times the square root times the derivative of the inside. Oh, and don't forget the negative out front like I just did. So the derivative there is negative 2x. So if we multiply those together, we get g prime of x is 2x over 2 times the square root of 5 minus x squared, and the 2's cancel. So g prime of x equals x over the square root of 5 minus x squared. Okay, so now what we care about is when is this equal to 0? And the answer to that is the only time this will be 0 is when x equals 0, which is one of our endpoints. So in this case, we only have 2 things to check again because our critical point was one of our endpoints. So we've got 0 and we've got negative square root of 5. If we plug 0 into the original function, we get negative root 5. And if we plug negative root 5 into the function, then we get 0. So this would be the minimum, and this would be the max. Okay, so once again, go and take a few minutes, pause the video, and try these problems here on the next page. And then when you're done trying them, you can start the video up again, and we'll go through the answers. Okay, so now that we've given these a try, let's run through them. So step 1, as always, right, is find the derivative. So the derivative of f prime of x is negative 1. So there is no critical point, right? Because that cannot equal 0, right? If f prime equals negative 1, it can't equal 0. So that means, once again here, we just need to check the endpoints. So we've got negative 4 and we've got 1. So if we plug in negative 4, we get 0, and if we plug in 1, we get negative 5, so the maximum would be at negative 4, 0, and the minimum would be at 1, negative 5. Okay, so that's the idea. So let's try these last two. So the derivative of 4 minus x cubed is negative 3x squared. If we set that equal to 0, we will find a critical value, which will be at 0. So x squared equals 0. Divide by negative 3, x squared equals 0, so x equals 0. So here, that's in our interval, so we need to check all 3 values. So we've got 0, negative 2, and 1. So if we plug in 0, we get 4. If we plug in negative 2 to the original function, we get positive 12, because negative 2 cubed is negative 8. 4 minus negative 8 is positive 12. And if we plug in 1, we get 3. So the minimum here is 1, 3, and the maximum is at negative 2, 12, because the largest y value is at negative 2, the smallest y value of the 3 is at 1. Okay, and then one last problem here is a trig one. So we do the derivative f prime of theta of tangent theta. The derivative of tangent is secant squared theta. So we can try and set that equal to 0. But as we discussed before, so that would mean secant of theta equals 0. But as we discussed earlier, There's no way for secant to be 0 because it's 1 over cosine. So if cosine's 0, then it's undefined. So that means there are no critical points. And then, so we just need to test the endpoints. And let me be a little more precise here and use the correct variable. So theta. So theta could be negative pi over 3 or pi over 4. So tangent of pi over 3 is root 3 over 2, negative root 3 over 2 over 1/2, so negative root 3, and tangent of pi over 4 is 1. So this would be the maximum, and, backwards. Negative pi over 3 comma negative root 3 would be the minimum, and pi over 4 comma 1 would be the maximum. Okay, so that's it for section 4.1. Check back later for more videos